Net primary productivity is the production of biomass. Here, we'll look at patterns of production after heterotrophic utilization of organic matter has occurred. This is net ecosystem production. On short timescales, GPP, gross primary productivity, and respiration typically dominate the carbon balance of terrestrial ecosystems. So, on short timescales, the major fluxes of carbon are photosynthesis and respiration. The balance between the two is net ecosystem production, NEP. And NEP is important because it's an estimate of carbon accumulation over time. So, two different formulas for NEP. The first is GPP, which is all the photosynthesis that happens, minus ecosystem respiration, or NPP, the amount of biomass that's produced, minus the amount of heterotrophic respiration. So here, ecosystem respiration is the balance of plant and heterotrophic respiration, and the difference between GPP and NPP is the respiration by plants. So net ecosystem production can be thought of as how much photosynthesis there is after you subtract out all of the ecosystem respiration, or how much biomass is left after heterotrophic respiration has occurred. Now there are daily and seasonal patterns to carbon exchange. So on the top we have carbon inputs, and on the bottom carbon losses. Here's a daily time scale going from midnight to noon to midnight, and this might be a typical pattern of photosynthesis. Now along with that, NEP is going to be slightly offset, but have a similar pattern. And the difference between the two is our ecosystem, so ecosystem respiration. So the difference between GPP and NEP, again, is the same as here, our ecosystem. And those might be a typical daily pattern of GPP and NEP. Now, the seasonal pattern is similar but slightly different. GPP peaks mid-year and then declines. And again, this would be for the northern hemisphere with the highest amount of GPP during the middle of the season. And then NEP is going to increase and then decline. But again, you can see that it's offset. There are periods when you have a negative NEP right here during the year. And that's times when there's more respiration than you have photosynthesis. And then later in the season, you can see that there's a longer time when ecosystem respiration is still high and GPP is low. And we talked how in a seasonal system that you can get a lot more respiration in autumn than you do photosynthesis. So this might be the curve for NEP, and the times of greatest carbon accumulation are going to be mid-season. And then after that, your carbon stocks would decline as GPP goes down, but ecosystem respiration stays relatively high. So looking at these curves, the first thing I would do is take a look at GPP and get to know the pattern of that, and then think about ecosystem respiration and when it's going to be highest during the day and when it's going to be relatively high during the year. That offset, the difference between the two, gets you NEP. So GPP, our ecosystem, and EP are the balance between carbon inputs and carbon losses. Now all of this to a certain degree is an abstraction, and it's very hard to measure all the components of GPP, NEP, and ecosystem respiration to get perfect measurements of each of those. Empirically, what happens is that we tend to measure net ecosystem exchange, which is the net exchange of carbon at the ecosystem scale. So we don't take a look at the components of the two as much as get the net exchange, whether there's a net loss or a net gain of carbon. And we don't necessarily so one way to do this is that if you had an ecosystem, you can put a chamber over it. You'd have plants growing in it, and you'd have respiration that would be happening, and you could take a look at the CO2 going into that and the CO2 coming out of it. If you could put a big chamber over an ecosystem. Well, putting a chamber over an ecosystem has been done before, and it's not a bad way to do things, except you change the microenvironment too much. So sunlight comes in and it tends to get hot inside of a chamber. Also, when you have evaporation, it's lost at a slower rate when it's inside a chamber than out. And so the humidity levels tend to be a little bit higher. This here is a station that allows us to measure net ecosystem exchange. There's a couple different components here. There's a sonic anemometer, which measures both wind speed and direction, so we can know whether a given parcel of air is coming down or going up. And so air that's circulating through the system, some of it's circulating downwards, and that tells us kind of the CO2 concentration up above the ecosystem. And then we've got some parcels of air that are moving upwards. And this is all associated with turbulence that happens in the ecosystem. So that way we can know the CO2 concentration of air going to the surface of the ecosystem and the CO2 concentration of the air that's coming out of the ecosystem. Now, these CO2 concentrations are measured here, and this is an infrared carbon dioxide measure, and it can measure carbon dioxide in the airspace right there. So all we have to know is the CO2 concentration going in, CO2 concentration going out, how much air is exchanging. And once you do that, you can get a good measurement of carbon exchange at the ecosystem level. When we take a look at CO2 flux from the ecosystem to the atmosphere, there are different patterns that we see across ecosystems. Here are some of the patterns of net ecosystem exchange across different ecosystems. So on the x-axis we have time going from January to December, and again this is for a typical northern hemisphere ecosystem. On the y-axis we have net ecosystem exchange. So on a daily basis, how many grams of carbon per meter squared are either being gained or lost. And in this case, a negative number represents a flux to the ecosystem. A positive number is a flux out of the ecosystem. All right, so 0 means that you have a balance of respiration and photosynthesis. Negative number means a net acquisition of carbon. Positive number means a net loss, more respiration than you do photosynthesis. 0 is the break-even point, and if we follow these triangles right here, which are deciduous forest, you can see there's a lot of respiration, and then it declines. And that break-even point right here happens somewhere in late March, which is typically when the forests are going to start to produce a lot of leaves and start photosynthesizing. Peak rates of photosynthesis are mid-season, June and into July. And when we have that, we get to a certain point when you still have net acquisition, but that rate of net acquisition is declining until you get to the point where there's more respiration than photosynthesis, typically when these forests are going to lose their leaves. So that's deciduous forest, and you can see that that had the highest rate of net ecosystem exchange, gaining somewhere on the order of 5 grams of carbon per meter squared per day. So it's going to photosynthesize on a net basis 5 grams more carbon than respiration that occurs, both plant and heterotrophic. Now crop systems are pretty similar, and I think at another end of the extreme we can take a look at grasslands here, or shrublands such as, these are probably chaparral, that just don't have a really high rate, and you can see even midsummer that they're a net loss. And this is probably Mediterranean shrubland that's going to have a gain of carbon in the off-season, what we consider the off-season, the winter wet time, and the hot dry time is going to be a net loss. So different ecosystems have different patterns of net ecosystem exchange, and they tend to follow the seasonal cycle of leaf area production, with differences in respiration and photosynthesis generating some of the other patterns that we see.